Hello, everyone, and welcome to this MPS EMI webinar sponsored by DigiKey. Today's webinar sheds light on key EMI issues and concepts when it comes to power supply design, and it's part of our ongoing webinar series. All of our webinars are available for on-demand streaming on the MPS website at monolithicpower.com/webinars. We'll be adding today's episode in a day or two, so expect to receive a follow-up email with details. Now, all attendees are on mute for the webinar, so we ask that you submit any questions through the Q&A button that you'll find in your Zoom application menu. We'll cover these at the end of the webinar. And now I'd like to turn it over to our first speaker, DigiKey's VP of Applications Engineering, Randall Ressel, who will give some brief remarks. Randall, over to you.
Thanks, Alan. You know, there's a slide, if you could pull that up. There are at least 4 factors to consider when designing a product. And electromagnetic interference and susceptibility is a loaded topic for a lot of people. It intimidates a lot of people. So I just want to point out that at least these 4 attributes can be considered when you're about to undertake a design. One is end application completeness. You can buy an end product that performs the total function, or you can design at the chip level. Now, of course, the technical breadth required to use or incorporate that technology, you need a lot of technical understanding to design at the chip level. There are EMI and RF issues and all kinds of board layout concerns. And on the other end, you're going to be paying more, but the whole unit is done and working. So you've got a product cost consideration. And then the final is the development cost. It'll take days, weeks, months, quarters to develop a product on your own versus you can get one when you're complete, in a complete product form also. Now, what's happened over time and what DigiKey is doing, next slide please, is to stock and fill in this range of product. So what's happened is modules have become very popular, and beyond that, entire boards. And so these are not complete products. They normally have to be enclosed in something else. But depending on what your abilities are, there's a whole range of product that you might want to choose from. Next slide. Now, what I've got on this next slide here are 2 graphs. The one on the left uses the left and right-hand axes. So the red shows quantity over time, and these are parts that DigiKey stocks, and these are essentially the sales results. And then the black bar are sales. Now, what I've done is I've normalized it to 2014 on the right-hand graph, and so you can see the quantity of boards is going up dramatically. It's interesting that I find customers who buy the chips that are on modules are also buying the modules. And I ask, why is that? And what it amounts to is that today's modules and boards are kind of like yesterday's chips. They are getting to be very complete and can help someone get to market faster. So my last slide is to show. And so the fact that the quantity is going up, but the revenue is going up slower, tells me that the boards are getting less and less expensive. The modules, the popularity of those is driving costs down as more people use them. So you can see that boards under $30 drive the bulk of DigiKey's revenue on small boards. And it's a good alternative. So don't just think that you have to buy a completely end finished product that's going to cost a lot. And on the far other side, you don't have to do it all yourself from ground zero. There's a continuum of product, and all of those are available from DigiKey. So I'm going to turn it back over to you, Alan.
So Randall, would you say that this is a good way to test the market?
Totally. It turns out that those modules, what we find is that companies will start and get a product into market. And if they've got a home run, then they can go back and decide to design at a lower level. So what we see are changes in purchasing patterns. And it's, I think, enabling more companies to make more products. So there's an explosion of small company development today because I think they're able to get the expertise of someone else in a cost-effective form, like in a module. And I think EMI is a great example of difficult technology that you can buy already packaged.
Very good, Randall. Thanks so much. So folks, on that note, let's go ahead and jump right into the details of EMI as it pertains to power supply design. And for this, I'm going to turn it over to our senior FAE and resident EMC guru, Christian Cook. Christian, over to you.
Hello. I'm about 30 years in the industry and most times working on industrial, medical, and automotive power supplies with all these EMI issues and so on. So today we talk a little bit, I want to talk about EMI of switch mode power supplies. And first I will dwell a little bit what a fixed frequency power supply puts out as a spectrum. I will go over the MPS module construction because that's also impacts the EMI performance they have. And I will go into the EMI disturbance sources with some examples. And how you can counteract these disturbances, in one case magnetic disturbances, also the electric disturbances. Then I talk a little bit about spread spectrum and its benefits and the impact of switching frequency. And last, I will go over the Q&A. As Alan already mentioned, you have a Q&A button. So during the speech, if any questions come up now, use that button, put your question in, and at the end of the seminar here, we will go into that. If you look on a normal switcher, a fixed frequency switcher, it has a comp-like spectrum. Now, so it doesn't prefer a certain frequency, but instead it gives switching frequency and all the harmonics. Here on the left side, you can see it goes from 1 megahertz to 300 megahertz. That's 5 dB per division, so it's fairly flat. Now, so you will see the switching frequency and all multiples of the switching frequency or the harmonics. If you go higher up from 300 megahertz up to 1 gigahertz, you see around 500, 600 megahertz. At a certain point, the slope goes down, so it's not flat anymore. Now, so the energy of these spurs, the energy of the edges get out of gas. And here I can see we have a fifth order slope where it goes down. But this slide still tells you that any switchable power supply design is actually a 1 gigahertz RF design. So you have to take care now that you do not get too much energy out in the universe. And how you do that, we will talk a little bit. Okay, there are several sources of EMI coupling into the universe. And typically one of the biggest problem is directly conductive galvanic. So any voltage noise source you create with your switching regulator will transmit it via the input and output cable, load cable and input cable, acting as antennas into the universe. Now, so that's looking like a perfect Hertz dipole antenna where your RF voltage source is just your switching regulator. Now, so what can you do about that one? Now you have to make this voltage source as low as possible. Let's dwell a little bit how MPS modules are built, because that has a big impact on EMI. And yeah, that was the short introduction. I think these commercial can tell that much better than I can do. The thing is that actually a module gives you an additional layers and is very compact. Now, so inductor, switch mode regulator, decoupling capacitors are much closer than you could do that on an individual board. And for that reason, they are typically performing a lot better on EMI. And we will dwell a little bit into it. Why is that? I will take an example of a module that's a pretty tiny 3 by 5 by 1.6 millimeter module. We provide with a maximum 36 volt input voltage, can put out 1.2 amps. Actually, in this shape of package, we have a lot different modules, and that's pretty typical. On the left side, I have the pin out, and you can see we have the output pins, and there's also switch pins. Normally, you don't need on a module the switch pins. However, the module is constructed, as you have seen, with the inductor inside here, and here in this area, the IC is inside. And that has some bearing if you want to make a very low IQ design. First, we made a design which is more thermally optimized. So you see from the ground and V out and V in a lot of VRs. So we try to get the thermals out. However, that has a little bit drawback on EMI, as we later see. So here you can see the top layer. Now see a lot of copper. That's the V in trace, local ground trace, the out trace, and that's auxiliary stuff. Layer 2, and that's common for a pretty good switch mode layout, is solid ground. Now, however, we have the power ground here connected with a lot of vias. Third layer, usually the auxiliary signals like enable, power good, and the other stuff, what you need is routed V in and V out. And on the bottom layer, we have an EMI filter because it's a 36 volt part. We add an EMI filter as you would typically need on any 24 volt industrial or 12 volt automotive, which is abstract 36 volt designer to show you the EMI performance. In addition, I made from the same module a second layout where I did not optimize so much for the thermals, but I did optimize a little bit more for EMI. And that differentiates itself a little bit, that I have an V in and local ground areas on top. The output goes underground. Now here's that's a picture. As usually, if you make the first layout, you see a yellow wire for enable, which you are missing. So that's a typical stuff that happens. And if you look through this board, you see in the second layer, there's not a solid ground plane. No? So here I have a ground area under the input capacitors, input decoupling, and a little bit under the IC. Now there's an other ground area below the inductor. And if you look at the third layer, we see that there's only a single connection on the total ground plane to the ground plane or the local ground plane in the second layer. Now, so these vias are all still ground, but they are not connected. And that goes further in the fourth layer now, where I've opened also all the local ground layer vias. Now, so it's definitely not thermally optimized, but it's better on EMI. How much better now, we will see. So go back to the normal thermally optimized design. You see from 150 kilohertz to 108 megahertz conducted EMI. That's fundamental, and the harmonics go up. And typically, especially in the above 30 megahertz area, it's pretty difficult to filter. Now, I mean, it's not looking real bad now, but you see 25 dB, 30 dB microvolt of spurs. One of the reasons that we see so much spurs here is that the input decoupling filter is not really optimized. And so we see a second order filter with a first ferrite beat as inductor, a second inductor, and we have two decoupling capacitors which are very close by. If we just move these decoupling capacitor to another location, we already see now that we can get several dBs, especially in the high frequency range. So I get back and forth. Now you can see now that that thing improves it. And even if you completely remove these CN4, it's get even better, no? Which shows you that sometimes you can remove components and stuff improves. Now it might be a little bit surprising, but very normal if you do EMI work. And if I move these CN4 to the top side, close to the decoupling, we get a further improvement on EMI. Now, so even with an existing design, you can improve it now if you improve a little bit where you place your filter components. In general, what you always should do, if you have an V-in on a buck regulator and decouple it locally, if you go to the input filter section, the first element of the input filter section you see from your switching power supply should be an inductive component, be it an inductor, ferrite bead, or whatever. Do not put a low impedance capacitor in your filter area, because that will screw up the low noise requirement of your filter. It will introduce a lot of input ripple. You want to locally decouple into your filter section. So make a clean cut between your filter area and your power supply area, and the component which goes from this area to that area should always be an inductor. So take the same part, same load, input voltage, and everything with the more EMI optimized design. So same switching frequency. We already see that under conducted emissions, we are 15 dB better. No? So we are well below any automotive limits. No? So industrial limit, don't worry, no? They are way higher here. No? So that are very tough automotive limits here. We are around 10 dB microvolt. Now, so that design is already much quieter in the FM range. If we compare that now to the non-optimized, then we'll see, okay, now so we got 10, 12 dB more noise. In the low frequency range, radiated, we call it monopole, it's radiated measurement from 150 kilohertz up to 30 megahertz. It looks good, well below the limits from such a very small module, very small switcher. You wouldn't expect that you got any problems in the low frequency radiated area, no? Just because the area is too small, no, to radiate much. No? Okay. Also where we locate the scene4 doesn't matter much on the low frequency side, on the monopole thing. If we look on the high frequency side from 30 megahertz up to 1 gigahertz, you see now that the thermally optimized design gets, I would say, sort of noisy in the 30 dB microvolt. And so you get a lot of radiated division emissions. And just if you relocate Xene4 to the top side, now you get a lot of improvement. If you go to the PCB2, that is the EMI optimized one, you see now that on the high frequency, it's very much quieter. What's left is one resonance, and this resonance is mainly due to the 1.7 meter harness. Also, it's here in the 80 megahertz range. You can check on that if you make an additional measurement just with a just shorter harness. Now you see now that the resonant point goes up. Now, so it's really in harness resonance which moves that point here up. Okay, what sources or other sources do we have? I mean, what I showed, it was a pretty good example on conducted source, on a galvanic source, but you also have between components capacitive coupling. So especially if you have components which move a lot in voltage. So think about anything which is hooked to the switch node, like boost capacitor, inductor. They bounce around voltage-wise, and they can couple in your EMI filter, for example. In addition to that, you will have magnetic coupling or transformer coupling. So the magnetic will couple into the next partner, so that are actually transformer windings. Magnetics are always created by currents. So currents through capacitors form a magnetic field, and that couples into another. So special capacitors are pretty good magnetic radiators. And last but not least, you can directly electromagnetic radiate. So if your components are from the size in the order of the wavelengths, then they can radiate pretty good. That's typically not that much the case on a switch mode power supply design, because we learned that below or above 600 megahertz, there's not much energy, and we have usually pretty small components which are not very effective electromagnetic radiators. But on a PCB, a complete PCB, you easily can have 5 or 10 centimeters of traces which could directly radiate. Typically, on a switch-on power supply, you have either magnetic field sources, so current loops, capacitors with ripple current, or you have electric or capacitive field sources, which could be the switch node and the top of the inductor. Now, the electric field sources are quite high impedance. The magnetic field sources are low impedance, typical here in the milliohm area. However, if you have a receiving antenna which has a distance greater than 1 divided by 2 pi wavelengths, 2 pi lambda, then regardless if you start with a magnetic or electric field source, if converts itself into an electromagnetic wave, and from that point on with your receiving antenna, you cannot actually differentiate what the source was from. From here we have far field. To get an idea, at 30 megahertz, far field starts at 1.6 meter. 100 megahertz is already 50 centimeters. So at 100 megahertz, if you are further apart than 50 centimeters, you cannot distinguish with your receiving antenna in the EMI chamber what type of field source the culprit is. So you have to go with much closer with near field probes to figure out what the source is. If you think about a small power supply with 1 watt running at 1 megahertz, and if you have that really matched to 50 ohm impedance, that would be an 147 dB microvolt source. So way higher than any limit you can dream of. So if you think at 100 megahertz, that would still be minus 10 dBm or 97 dB microvolt, if you assume that the harmonics go down with 20 dB per decade, which is true for rectangular waveform. Yeah, so even that is much higher than the typical limits. So we will need about 80 dB attenuation. So in order to get your power supplies through typical EMI certification, you need an damping or mismatch of 80 dBs or more. So that's what you have to do with your power supply design, that you do not make a radio station. So you have to mismatch the source from the universe. If you think about filters, it's pretty easy to get these 80 dB damping. So I've just simulated a filter with first order parasitics. So the inductors have parallel capacity, the capacitors have series inductance and some series resistance, and even with that you get easily at 150 megahertz with that second order filter 80 dB of damping. However, if you measure a real world filter, so that's from a board with a vector network analyzer, you will find that especially in high frequencies, you will get much less damping. So at 100 megahertz, I just measured about 64 dB, so 15 dB less than what's actually needed. So it's actually quite difficult with a real world filter to get good damping in the high frequency area. So that's the noise floor if you do not believe my measurements. So how can you improve your filters if you do them? We learned now that capacitors couple with each other magnetically or in a transformer way. So in order to get a good filter action, just move one capacitor from the other with distance, or turn it 90 degrees. So good distance is good. So here is a good example of a fourth order filter with 2 inductors, 2 capacitor sections. Typically, it's pretty good if you make an RF layout with capacitors in line, ground on the outside, VIN on the inside. So you have actually compensating current loops and compensating magnetic field here. And move both sections apart from each other, that this capacitor does not magnetically couple into this capacitor here. What you can do actually to attenuate magnetic field source, I made a little experiment with an inductive stove. Inductive stove runs at 22 kilohertz. So I have an omega loop, and there's actually a rectangle loop 10 by 10 centimeter where you get say roughly about 100 amps and 22 kilohertz. That inductive stove operates. I have to put a pot with water on it and switch it on. And to visualize the magnetic field, I just put an aluminum foil over the loop. And if I put a plane, a short circuit plane, a ground plane from below, you see that the flying distance of the aluminum foil goes lower. So actually, even a plane from the other side will diminish the magnetic field you create. And same goes even if you go from the other side. Now you will diminish the net magnetic field if you short circuit it. And that's actually the operational mode of any plane you put under your hot loop, which creates a lot of magnetic noise. That typically shows you that on a PCB with multi-layers, you can reach a lot of attenuation on the magnetic side if you put a solid plane under it. I have a simulation where you look from one side in a PCB. So I have here two current strings here 10 millimeter apart with 1 amp each, and I have a magnetic sensor about 8 centimeter apart. And if I do not have any conductive material here, I have it 10 millimeters apart at a reached plus 23 dB. Now, so let's run a movie actually with the filter. So if I have the plane distance of 2 millimeter, now I get minus 46 dB. If I remove the ground plane, I check that on 0 dB with 6 millimeter. If I move the strings apart by 10 millimeter, I get plus 23 dB. And if I move them back to 0.6 millimeter, which is realistic for a hot loop, and if I get now my ground plane closer and closer to my hot loop, so here at 2 millimeter, that's a typical situation which I have in a 2-layer board, I get minus 46 dB. If I go with my ground plane or my plane now closer to my hot loop, like 0.2 millimeter, which is typically for a multi-layer, now I get 86 dB attenuation. So you reach a lot of attenuation if you make a solid ground plane. And it's also clear that the multi-layer board where you get your plane 0.2 millimeter to your top traces performs much better than if you have them only in a 2-layer board where you have 2 millimeter or 1.6 millimeter distance. If you typically want to make a very low power supply design and you have a multi-layer, like 4 layers or more, now you start with the top layer where you have the power component routings. So you have the inductor to the switch connected, the VIN connected to the input capacitor. And in the 6th layer, locally, you make a solid ground plane here. But on the bottom layer, you make a quiet ground plane and you hook these noisy ground only at one via block with this area together. The auxiliary signals are also not connected now that you do not introduce from your noisy ground area current signals in your quiet ground area. And typically in your quiet ground area, you put your EMI filter, because EMI filter, either you have distance or you put it on the other side, you make it very quiet. If you can't do it, now there's also a possibility you shield these things completely. Now I will later show you in a module example how that performs. So if you go back to these EMI optimized example, we can see that the hot loop, which is on a buck regulator from the input capacitor over the top switch to the bottom switch, so that's a fully switched loop which creates the most magnetic noise. You can actually follow that. Now here's a ground connection. So for this capacitor, now it will flow through the IC, goes at the corner of the board, goes here into the capacitor at the ground, back here from the corner to the board to that area. And so that's the loop of this decoupling capacitor. From the other decoupling capacitor, it will go from the IC over these via through the ground plane into the capacitor and then back to VIN. So that's symmetrically decoupled, even if you have only a single V-in pin on a very small module, and you can get it very quiet. And you see here, this is a complete local ground plane under it, where this eddy current would actually cancel the magnetic loop now, which that creates. If you want to get a step further, MPS also has actual metal can modules, which are in this case 12 by 12 by 4.2 millimeter. That's in 36 volt, 5 amp parts, MPM 3550 on a board. Now we only need an additional input and output capacitors. And we have on the back side also an additional filter for that. If you actually measure the performance, we'll see, okay, it's above 90% efficiency. And beside efficiency, most times more important is what the thermal load, what the total power loss of my solution is. Power loss will be input power minus output power, so everything which creates heat. And we see that at 5 amp load, we are still in the 2 watt range, which you can easily handle with such a large package. If you look on the EMI, so I have measured here the conducted EMI from 150 kilohertz to 108 megahertz. And you see a special in the high frequency region above 30 megahertz, where it's typically very difficult to get a lot of, say, attenuation, that it's extremely quiet. Now, I have to add that actually I use a low noise amplifier, which has a noise figure of about 4 dB, which means that a 50 ohm resistor at room temperature probably read here minus 18, minus 20 dB microvolt. So we have a module which puts out 1.8 amp at 3.3 volt from 12.8, which is maybe 10 dB worse than a 25 ohm resistor, just the thermal noise a 50 ohm resistor puts out. So that would be very difficult if you want to achieve such a good EMI performance with a non-module design where you have much larger loops. Radiated emission in the low frequency range, now see almost nothing. So, and here that's 0 dB microvolt. So that's a special setup. Typically, if you are in an EMI chamber, your noise floor will be something here now, so you wouldn't see any, you would see nothing. Even on the high frequency range, radiated emission 30 megahertz to 1 gigahertz, you don't see any signal. So the blue one is what I measure. The gray one is actually the noise floor, and I have a GSM base station in my surrounding, or I don't get it absolutely quiet in my system. However, typically the noise floor of a normal EMI measurement system, a normal EMI chamber, would be here in that area. So we are well below what you typically would measure. Then I want to talk a little bit about what you can do in addition if you go away from fixed frequency into spread spectrum. You can assume that a fixed frequency switcher will give you a fence, a comp, with all the harmonics. And if the EMI receiver goes with its resolution bandwidth, which is up to 30 megahertz, 9 kilohertz, above 30 megahertz, typically 120 kilohertz, you can assume now that the receiver bandwidth convolutes with your comp, which widens up the comp by the receiver bandwidth. So depending where your switching frequency is, you still have an empty space where you a fixed frequency switcher don't make noises, where with spread spectrum, you could hide some energy. And if you know that, it's pretty simple to give you an equation what a perfect spread spectrum, which makes out white noise, can get as attenuation compared to fixed frequency switcher. And you see at a 2 megahertz of up to 30 megahertz with 9 kilohertz resolution bandwidth, the maximum a white noise switcher would achieve would be minus 23.5 dB. Since above 30 megahertz, the resolution bandwidth is 120 kilohertz, you only get 12.2 dB at 2 megahertz. At 400 kilohertz is only 5.2 dB versus 16.5 dB. So yes, spread spectrum achieves attenuation, additional attenuation. However, it's physically limited. Also, that everybody should have in mind what you can do. The good thing about spread spectrum is that it works independent of all the other methods I told you today, so shielding and so on. So with spread spectrum, you always add additional attenuation, and it typically you will get a little bit free spread spectrum on the high-end harmonics. You can think if you have an, say, 1 megahertz switcher, and the phase noise at 1 megahertz will multiply by 100 at 100 megahertz. And so if you have a typical switching regulator, which has some phase noise, and even COT switchers have more typically phase noise, they give you some natural spread spectrum. However, if you force your system to synchronize on a crystal clock, which has very low phase noise, then this benefit goes away. So synchronizing with a very clean clock actually can damage your EMI performance. So don't be surprised on that one. Next, what I want to talk about is the effect of the switching frequency on EMI. In general, on every switching cycle, on every switching edge, you get a certain amount of energy, which on EMI energy, which means as more often I go through these switch cycles, as more EMI energy I create. And so you can easily assume that doubling the switching frequency will double the EMI energy. Doubled EMI energy is 3 dB more because we are in a power area. So we get with double the power, 3 dB more. So you could see now that with doubling the switching frequency, you only make your EMI 3 dB worse. However, on a fixed frequency switcher, you have an additional drawback that with doubling the switching frequency, not only you get 3 dB more, but you only have half the bins, half the areas where your EMI energy concentrates. So in a sense, you get with the fixed frequency switcher, by doubling the switching frequency, 6 dB worse EMI energy. So it's not a very good idea just to go higher with your switching frequency, just for the reason to get your stuff a little bit smaller. So you get, by doubling of a fixed frequency switcher, 6 dB more. So if you go from 500 kilohertz to 2 megahertz with 4 times increase, you get 12 dB worse EMI. And even with a perfect white noise spread spectrum switcher, you still would get 3 dB more energy per doubling. So that's a problem you will get just increasing the switching frequency. So what you have hopefully learned today, multi-layer boards offer superior EMI compared to 2-layer or single-layer boards, because you have your planes, which with eddy currents attenuate magnetic noise much closer to your excitation sources, to the planes where actually the current flows. We learned that you should keep distance between the EMI filter and PSOU components. If you can't, you have to shield or buy a nice metal can module where we take care of the shielding. Use a ground plane in the second layer if you have a multi-layer. You can make cuts in the noisy parts if you exactly know what you're doing. However, be careful. You should know what you're doing. Modules are quiet because they have small current loops, small components, and you get 3 added layers with them. And they had internal layers, as I say. Metal can modules offer lowest EMI because they give you additional the shielding of the metal can. And EMI goes up with switching frequency. So keep the switching frequency as low as practical. And spread spectrum adds additional EMI performance, and the best performance you get below 30 megahertz, or the best additional attenuation you get below 30 megahertz, because there the EMI resolution bandwidth is 9 kilohertz, so which gives you a better attenuation. MPS puts a lot of effort in optimizing the EMI performance of our demo boards. So we have already an EMI test center in Hangzhou, and additional labs are currently built in Germany and Detroit to support our customer base. In addition, I think thanks for attending the webinar. I will go over it to Ellen, which adds, I think, a little bit a few words.
Christian, thank you so much. Fantastic. So folks, just a reminder, there is a Q&A icon button in your Zoom application. So please use that to submit any questions to Christian. And with that said, we do actually have already several questions in the queue. So let's go through these. The first one submitted towards the beginning of the presentation is, what is the use of maximum vias on plan?
Okay, I try to answer that now. So typically, there are lots of limitations. Most times you can't use or should not use vias below planes or areas under an IC, because that gives polarity issues. Other than that, typically there's nothing wrong with using a lot of vias in your area, but you have to make sure that you do not connect noisy areas, noisy planes, noisy ground planes with quiet ground planes. Other than that, typically more vias are better than less. So typically on a good board, I make a fence of vias around the outside, now that I make sure now that no corner is really radiating. Now, so typically there is no other limitations on vias that you could use, and typically vias in parallel gets inductance down. So if you connect planes or something, more vias are always better. Now, they cost a little bit, but that's typically not a concern.
Okay, the next question actually was revisiting one of the earlier slides to just have a little bit more elaboration or just cover again the comment about I think this was the input filter, the inductor followed by an electrolytic capacitor instead of a ceramic capacitor.
Oh, actually, these electrolytic capacitor is not doing much on the EMI side, and because electrolytic capacitor has several hundred milliohms ESR, but it typically damps audio resonances you get. And one very safe way to destroy a demo board is if you, for example, have a 5-volt switcher and you hook up these 5-volt over 1 meter banana cables to your already switched on 5-volt laptop supply. You plug it in, and the board blows up because you have ceramic input capacitors and the free 1 microhenry inductance of your 1 meter banana cables make a very high QLC resonance circuit with resonances around 5 volt, which means between 0 and 10 volts. 0 and 5 is not the problem, but from 5 to 10, that might blow your board. And with an electrolytic capacitor, you damp your high QLC tank, and you do not get these overshoots if you fill around with banana jacks. You have the same thing if you have an industrial system where you might have plug-in things. There's always there could be intermediate contacts and so on. So electrolytics are very good to give additional damping in the audio range. Additional thing is that the actually high aluminum case gets an additional, say, electric shielding between areas. Now, so you could place actually an aluminum capacitor between your EMI filter and the switcher to get some additional shielding in between.
Okay, next question. How would you try to solve the EMI problem caused by harness resonance?
Okay, the thing is that you have to get the harness resonance lower or higher. Higher, if you have a given harness, it's probably difficult to make it higher. So easiest thing is to make it lower just by adding additional inductors. So add some whatever filtering inductors or so on to move the harness resonance down. You can try to damp it a little bit now, and there also the aluminum capacitor comes into play, or you could use actually capacitors which have additional series resistance. So the thing is, try to get the Q out of the system or move the frequency down, or both. Now that's the chances you have if you want to get the resonance of your harness down. Up is very difficult, and then you have to cut your harness short, and most times your customer tells you how long your cable has to be.
Okay, thank you, Christian. So next question is, how do you calculate the decap value depending on EMI noise?
Yeah, most times you have more capacity than you need. No? So the EMI noise at the higher end typically is more dependent on the parasitic inductance of your ceramic capacitors, the magnetic field the capacitor puts out, the electric field your inductor puts out. And so it's more an area where you try to keep your physical size of the capacitors and the filtering inductors small and keep them apart. If you can't keep them apart, now you have to shield them a little bit. No? So you will be surprised how big differences are between a SPICE simulation, as I showed you, and a real measurement if you do. No? So go ahead and measure them with a vector network analyzer, and you get a really good feel what you get to it. It's not as easy as you think now to get good damping. But typically for the high frequency, I mean, it's more a matter of parasitics. On the low frequency, it's easier. No? So below 5 megahertz, actually SPICE works. No? So the parasitics are not that high. So there really you can, with normal simulation or just a sheet of paper and calculation of filter, get the results you can also measure. No? So there just you have to hire the components.
Next question is, on your earlier slide, when you improve the layout on PCB2, is there only one via connection between local ground on layer 2 and the ground plane on layer 3? Or maybe that was layer 4. Will that be good for DC current, and is there a good preferred location for this via connection?
Actually, on this plane, because it's only an 1 amp design, I used only one via. However, you can also use a via block with more vias which are close by, or a direct connection on the second layer, now where you go from the noisy ground to the close ground. But this connection should be on a place where you define where you want to have your quiet spot. So an area which typically should not be in the middle of the under the hot loop, a little bit aside from that, as this is the case.
Next question, how does duty cycle impact EMI and performance?
Duty cycle, it's pretty similar what you learn in SHU. You can make a Fourier transformation out of your duty cycle and you get actually your harmonics. So your duty cycle will not impact the high frequency, high harmonics, like harmonics number 30 to several thousand. That's not a problem. But you will see that actually on the low harmonics, the distribution of your low harmonics will directly depend on duty cycle. So you can make the experiment with a spectrum analyzer, or if you have an FFT software or whatever. So you will move your lower harmonics around if the duty cycle moves. And typically on a buck regulator, your duty cycle is given by V out divided by V in. So there's not much you can do about that. And that tells you how the distribution of the lower end harmonics are. But on the higher end harmonics, say 30 harmonics and above, a typical duty cycle has no impact.
Okay, next question, which you already partially answered. What's the ideal arrangement after the inductor to the VIN pin on the switcher?
Yeah, it should be underground now for not radiating. It's an inductive component, and then you go just to the input decoupling. Now, it could be on in an inner layer. You could put that on the top trace. I mean, that's pretty, say, a normal connection. And since it's inductive, it's not actually that noisy. Now, so you shouldn't have much ripple current on that. Now, so it's more a concern that you do not get too much voltage drop on that one.
Next question. Should there be two decoupling capacitors at the VN pin on the switcher instead of one high frequency capacitor? In other words, 0.22 microfarads or 0.1 microfarads?
If you can, two in line with the grounds out on the outside will actually get an cancellation of magnetic disturbances if you are further apart. You can think now that if an RF current goes through the inductors, if you are further apart, they will cancel out and you will get a symmetric zero line in the middle. Now. So if you have the space, two capacitors in line with V in the middle and ground outside are always better than a single one.
And Christian, is PFM or PWM better from an EMI point of view?
Actually, it boils down to be a sort of, say, spectrum. So thing is, if you have, say, a few bursts, the problem is that you get low frequency content. If you have, say, continuous operation, it doesn't matter. Then there's it's more a matter what phase noise your general switching frequency generator has. Now, other than that, no, it's more a low frequency audio problem.
And Christian, could you please re-explain why the EMI filter should be kept far away from the power supply?
Because the power supply has a lot of magnetic noise. So the hot loop is the #1 magnetic radiator, and that definitely magnetically radiates and couples into your filter components. So your nice, say, 80 to 100 dB filter attenuation drops down to, say, a few 10 of dB, if any, if you move your filter very close to the switcher. So that's the main reason that you want to have your filter in a quiet area away from the very noisy area directly at your power supply.
And why is ground stitching important along the board edges?
Thing is that if you have a board which has is 10 by 20 centimeters or in inches, 4 by 6 inches or so, if you have a lot of RF current going at the corner, it's actually a pretty good antenna, because here you for several hundred megahertz you have a very effective antenna, and you have a lot of ground stitching. You make sure that you do not have say RF current at the edges, but you have a solid ground. So typically the stitches don't cost much and might improve EMI performance, because it's very difficult to fight these later if you have forgotten that. There's a reason if you open up your older GSM phone and look what they did now, so you always see these stitches around now, so they don't do them just for fun now, so it's really helping the RF.
Now, does the module that you showed have UL or FCC certification? And do you have a recommended spot for the temperature measurement?
Okay, there are actually two measurements. I think UL, I'm not sure that that's more an issue about the package material if it burns, but FCC certificate usually get with a complete board. And I mean, if you we can do a measurement of our demo board and could get an FCC certificate for that, but that's no help, because you have to redo that in your instrument anyway. So that's not a matter. The demo boards we do to show you that you can get an FCC certificate, so that you do not get actually a problem. The best spot to measure temperature, they actually say three ways. Now, what one would be with an infrared thermometer to get the top temperature of the die. If you're interested in the die temperature, you could also put a thermocouple directly to the ground plane, or to the ground areas. You can actually solder it. And if you want to really get the die temperature, there's on some of our parts also the possibility that you actually use an internal diode and calibrate them to get really accurate dice temperatures. Now, but if you want to get more information on it, just ask a local FAE who will tell you the way to do that.
How about a recommended hotspot on the package when it comes to measuring the thermals?
I mean, the hotspot you get from yourself, that's typically in the middle of the switching IC. Now, so you could, if the inductor is very small, the inductor could also be a hotspot. But that should be the only hotspot in a switching power supply. Anything else gets hot now, then you had made a pretty poor design. So typically the switcher and the inductor are the typical two things. And most times the IC will get hotter than the inductor if you have a decent design.
Okay, now if I have to cut the noisy ground, how far away from the switching loop should I do that?
Yeah, since it's magnetic, it's actually an aspect ratio game. So as higher your components are, further apart you have to go. So it's difficult to guess and estimate, but from heights to widths, I would say a 3 to 10 to 1 ratio. So if I have a 2 millimeter high inductor, I should say 4 8 millimeters apart with my cut.
Okay, and here's a classic question. When using a higher switching frequency, smaller components can be used, which I assume would contain fields better. So what is the magnitude of the effect of switching frequency versus component size?
Yeah, that's a classic. So the thing is that doubling the switching frequency will, for same ripple current, allow you to cut the inductance of the inductor by half. However, if for the same current you cut the inductance of inductor by half, doesn't mean that the volume it's cut by half. It's only cut by a square root of half. So you get a diminishing return if you are going higher with your switching frequency. The second problem, and that's also a major one, is that actually for the same current, you still need the same copper area to get the DCR. You can get lower number of windings, but at a certain point now you can't make your copper thinner or your DCR losses go up. The third problem is actually that due to skin and proximity effect, the resistance of your copper goes up with switching frequency. And for fun, you should measure an actually inductor with an VNA and look what the real component of the resistance is over frequency, and you'd be amazed that even at switching frequency you easily have an effective resistance which might be 10 times 15 times the DC resistance. So also your loss terms of the conductive resistance in your windings go up if you go up with the switching frequency. I mean, you can go and make your switcher super conductive to get around that, but up to now, it's not practical to do that.
Christian, how do you measure the input impedance of a DC-DC converter?
The input impedance of a DC-DC converter is by definition negative, which means if I go higher with voltage, the current goes down because the DC-DC converter makes constant power output, which means that if efficiency is constant, assumed constant power input, and constant power input is actually a negative impedance. So it has the capability with its negative impedance to make an oscillator out of your input EMI filter. So you have to be a little bit careful and look that you still get some damping. And here also comes the aluminum capacitor into the play, because you want to damp your input audio resonance your input EMI filter creates. So that's something you have to keep also in mind, and you have to check for it.
Very good. Folks, we're going to keep going with the Q&A, so please feel free to keep submitting your questions. We still have quite a lot to go through. Just a quick note, though, that we are going to make this webinar available for on-demand viewing through our website at monolithicpower.com/webinars, and as well as a presentation in PDF format. I'd also like to take this time to remind everybody that we do have a broad global FAE presence, and we're available to come and provide you guys with more direct support. We also have a new virtual FAE program that is run out of our headquarters in San Jose. Please go to monolithicpower.com. You'll find a link for Contact Us, and use that. Feel free to reach out to us. We'd love to connect with you guys. So let's go back to the Q&A. The next question is the shield of the shielded modules connected to ground?
Yes, I think it is. In general, if you make a power supply and shield it yourself, the shield could be ground, or it should be something which does not move voltage-wise to ground. And so there's nothing wrong with connecting the shield to V in or V out, or a capacitor to ground, but it should not move, otherwise you do not get any E-field or electrical field shielding.
Now, Christian, how do we meet the Middlebrook criteria?
I assume that the Middlebrook criteria goes off to slope compensation, and that's a thing, I mean, in current motor regulators, we put in some slope compensation area, which puts usually an lower bound on the DIDT. No? So there is on, if you use duty cycles which are higher than 40–50%, there is typically for a given switching frequency and given input to output voltage ratio, a lower bound of the inductor size, that the slope compensation is still effective.
And to reduce the EMI, is it better to use in via a decoupling capacitor?
Oh, a decoupling capacitor should always be put on the top side. Now, so vias will add, there's a rule of thumb. Now, if you go through a complete PCB, it's about 1 nanohenry per via. Now, so you destroy the performance of decoupling capacitors if you push that current through the inductance of vias. Now, always put decoupling capacitors directly on the side, now where the traces are you want to decouple. Now, so don't use vias if you can help it.
Next question is how much modulation depth for spread spectrum is recommended? Plus or minus 3 kilohertz, plus or minus 5 kilohertz, etc. And I'd like to take this opportunity to let everyone know that we actually have a focused webinar that we did last year, specifically talking about the benefits of spread spectrum for EMC. Again, monolithicpower.com/webinars. Christian?
Yeah, typically you should use more modulation depths. So in a sense, what helps is actually the modulation index, which is the modulation depth divided by switching frequency. So if you have, for example, a 2 megahertz switcher or 400 kilohertz switcher, I would easily go with 10% of switching frequency as modulation depth and not the very little. Actually, the modulation depth goes linearly up with the harmonics you look for. However, for above 30 megahertz, you need higher modulation depth or higher modulation span if you want to have it anyway. No? So I would go higher if you can. Now, typically, plus minus 3 kilohertz or plus minus 5 kilohertz doesn't help much. No? So at 400 kilohertz, go plus minus 40 kilohertz or something in 10, 20, 30% of the switching frequency and not lower, unless you have a very special requirement.
Do you recommend the use of net ties to connect different grounds to separate noisy from clean grounds?
That's typically a more layout program issue now, that you do not mix up these things now. So that will depend on, say, the layout program you use now. So that's a question a layouter should answer. Now. I can't. Now you should make sure if you make cuts now that in reality you have them. Now that's a physical thing, and how your layout program handles them. Now, okay, your layout guy should answer that.
Okay, another classic question. Do you optimize rise fall times to meet EMC performance?
Sure, we do now, because I mean that's always a trade-off between efficiency and EMI. However, if you run a switch at 400 kilohertz or 2 megahertz, there's a boundary, especially if you're running low duty cycles or high V in to V out ratios, that very quickly your efficiency goes down the thing. So there's only so much you can do and so much efficiency you want to lose / heat you want to create. So I would say up to 50, 100 megahertz, it doesn't make too much difference, even if you slow down your edges. It's another issue if you are talking about really high voltages like offline power supplies or so. There you go to lower switching frequencies and you try to make your edges as slow as possible. But as long as you run 400 kilohertz or above AM 2 megahertz, there's not too much you can do. The slopes are in the range of, say, a nanosecond, 2 nanoseconds, 3 nanoseconds, but you can't make a 10 nanosecond slope on an 100 nanosecond on time. You would waste about 20% of efficiency and create heat for it.
How about long aspect ratio ceramic capacitors? For example, 0612 and 1206. Do they help with high frequency harmonics?
Yeah, the thing is that actually the idea of these wrong-shaped capacitors is to make the parasitic inductance smaller, and they work in that demand now that the parasitic inductance gets smaller as long as the shortest magnetic path is around these capacitors. So you either can use these odd-shaped or you can actually parallel normal ones very close, and they give pretty much the same effect. And you should keep in mind that actually a plane directly under the capacitor also reduces the parasitic inductance, because inductance is actually the magnetic field, the total integral of magnetic field created. And if you get some of these field away with eddy currents, you actually reduce the inductance. No? So answer is yes, they help, but you could also parallel them to get the same effect.
Next question, why cutout area provided in the PCB layout for isolation circuit? What is this effect exactly?
Yeah, it's the thing is that actually the noisy eddy currents you create in a local plane, you do not want to have them distributed to the outside, because current in any conductive, which is not superconductive material, will create voltages, and you do not want to have these voltages outside, that you have a voltage source in your harness between different positions of your PCB. Now, that's the reason that you can make cuts inside a plane to get a noisy ground plane area and a quiet ground area.
How does the trace thickness affect EMI?
Extremely little, because if you look on the skin effect, you already see that I think above 15 megahertz, it doesn't matter if you have 2 ounce, 1 ounce or ½ ounce copper, because the high frequency currents will concentrate on the skin on the outside, because that's the meaning of skin effect.
And do you recommend perpendicularly placed decaps?
Yeah, capacitors, they should be placed, say, in line, which means V in the middle and ground on the outside. So you should see lines and have the currents flowing in opposite directions.
Okay, on this one, on either a module or discrete design, is it recommended to remove the ground beneath the switch node of the inductor? Your ground planes seem to stop short of the switching area.
Typically, ground planes conduct eddy currents. So under inductor, there should be, at least in the second layer, a solid plane. So don't leave holes through all layers under the inductor that the magnetic fields can get through all layers. Now that would be a stupid thing. So at least in the second layer, there should be a solid ground or a solid plate under the inductor to shield the magnetics through eddy currents in that plane.
Any reference designs or application notes for effective EMI filter design?
I think if you look on our typically, say, automotive demo boards, like for the 4430, 43, 117, 15 or something, there will be very effective automotive EMI filters, and just grab the schematics of these demo boards and you will get an idea what they look like.
Yes, and on that note, folks, if you have specific automotive products that you are interested in from MPS, typically you'll find, and this is usually on request, that we'll have EMC reports available. Again, this is tested out of our EMC facility in Hangzhou, China. So if you don't find one, it never hurts to ask. All right, next question. The input MLCC of a buck converter resonates with parasitic inductances and the COS of the MOSFETs, and this can be seen often as a ringing in the switch node. Are there any alternative methods to prevent this ringing by adding damping without a snubber in the switching node?
Actually, these ringing, you get a parasitic inductance now of your layout. So what you can do is try to reduce the parasitic inductance of your layout. Now make your hot loop as small as possible, decouple it symmetric, use several capacitors, MLCC capacitors in an, say, inline concentration, or that you get the resonance frequency of that thing so high now that you do not see that much on the switch, that resonance on the switch node. On the other hand, it's probably not possible to get these ringing totally to zero. So something you will always see. And actually from the EMI side, you might see that a little bit on an EMI plot, but you can shift it a little bit. Try to keep the parasitics, especially the total hot loop area, the hot loop inductance, low, and use parallel ceramic capacitors in an inline configuration and symmetrically decoupling to get that slow. Typically, what my experience is in buck regulators, snubber network is pretty much a waste because you just add additional currents in the snubber, so it makes matters most times worse than it helps. On the other hand, on an isolated offline design, it's a complete other story. So here a snubber is necessary, but a normal buck converter, typically you shouldn't need some. You should really rethink your total layout that you get the parasitic inductance of your hot loop lower.
Now this is, next question is an extension of the rise fall time from earlier. Will this help to meet EMI performance at the megahertz frequencies?
It will actually improve in the several hundred megahertz frequency. Up to, say, 100 megahertz or 200 megahertz, there's not much difference by, at least on a modern buck converter. I'm not talking about some 500 volt IGBT something, but typically 400 kilohertz or 2 megahertz switcher with a nanosecond or 2 nanosecond fall and rise times. I mean, you will have edges which go into the several hundred megahertz areas. So up to 30, 50, 100 megahertz, you won't see much improvement with slowing down the edges.
All right, next question is sort of a fundamental one. So how do you select the correct value and location to solve or address buck regulator input and output rail EMI emission issues?
Yeah, so that means a general design question. So typically you get a spec sheet with input voltage, output current. From that, you have maybe further restraints that from a spectral area, you might have radio receivers or whatever. And from that, you pick a switching frequency, and you pick either an integrated switcher or a discrete switcher with external MOSFET, or you pick a module and you go with your design from there. Because at a certain point, you have to deliver probably a solution to your boss. So you only are limited to what you can physically buy. So I mean, it's typically use pretty much the most modern stuff you can get your hands on. So that's my recommendation.
Okay, next question. Common mode choke versus differential mode choke for EMI filter. Which is better?
I mean, if you can use a common mode choke, use one, because that's the easiest way to get very high impedance in your harness. So if you make an isolated design, that's most times the only choice you have to really pass EMI. On a non-isolated design, if you can use common mode choke, it's fine, but very often you have a lot of inputs and outputs. So your power supply input and maybe output is not the only connections you have to ground. You have also other, say, bus signals and whatever IOs. And as soon you have that, you can't use a common mode choke anymore, because a common mode choke also will start to isolate the ground of your power supply. So if you can allow your ground to be isolated, common mode choke is very good solution. However, in most, say, industrial and automotive areas, you can't use them because ground by definition will go also out of your unit on other cables, and it needs to be quiet, and a common mode choke would defeat that.
Now, is there a disadvantage to using aluminum poly instead of aluminum electrolytic capacitors for bulk capacitance?
No, it isn't. Just use whatever you get. Typically, poly has a lower ESR. You have to get some damping to damp the audio resonance, audio frequency of your input filter. If you use aluminum or poly, it's a design issue. So it's not my preference. I mean, you buy capacitor and you buy ESR. That's basically what it is.
And how does a snubber circuit work for EMI?
Yeah, typically a snubber circuit will load additionally the switch node, and with that slows it down. However, a working snubber circuit will take definitely a lot of additional current, and so it creates an additional hot loop. So the snubber circuit itself will be an additional EMI source. If you have an isolated supply, especially if you are filling with high voltages, high voltage swings, several hundred volts, sometimes there's no other way to slow that down. But in a normal non-isolated buck circuit, up to say 60 volt or so, most times you make matters worse using a snubber circuit.
How do we trade off EMI versus eddy current losses for inductors? Wouldn't eddy currents take a hit on efficiency?
The thing is, I mean, there are actually magnetically and electrically shielded inductors which have a shield completely around the inductor, and they work very effective on the electric field. However, they make typically, for example, on a 2 megahertz switcher, and 1-2% efficiency hit due to their eddy currents. You can actually make yourself a shielded inductor by just placing a conductive material not directly onto the magnetic material, but with a space of, say, 1 millimeter. So this 1 millimeter additional air gap between your shield and the inductor makes typically get the losses go away. So you have very little additional losses by your shield if you actually have an air gap between the inductive material, the ferrite or the molded iron powder and the shield.
And folks, our final question: can adding a series resistor on the switch gate reduce EMI? And is there any downside other than switching speed?
As it's typically a discrete switcher with discrete MOSFETs. And most times that's what you have to do as a last resort, that you have to slow down the switching action by a gate resistor. The downside is that not only the turn on speed is lower, also the turn off speed is lower. And if you look in a typical half bridge configuration, what you want to have is you want to grab or want to keep your MOSFET off, and there a gate resistor makes it harder to keep the gate actually down. So typically resistor in series with the boost capacitor is a more effective way, because that slows down switch on but keeps your low impedance gate drive for switch off. So a normal gate resistor is typically not a very good idea if you also have the option just to use a resistor in series with the boost capacitor.
Christian, I'm going to sneak in an encore question.
Sure.
Can a shield on the circuit actually make noise worse?
Depends where, if it's not actually connected to ground or a quiet voltage noise, it can make it worse. If it's just a shield which is hanging free in the air, not connected to anything, it can make it worse, because it will distribute the concentrated E field, electrical or capacitive field noise to a much wider area. So I think as soon as you hook it to a quiet voltage potential, typically ground or so, it usually improves things.
All right, folks, that's it for questions. I'd like to say a special thank you to our friends at DigiKey and Randall Russell in particular for sponsoring today's webinar. And of course, a huge thank you to our EMC guru, Christian Cook, especially for this record Q&A. And again, folks, this will be available for on-demand viewing. We'll send out an email after today. And last but not least, in sort of a thank you for attending the webinar, we're going to be sending you guys all a coupon code via email, and this will be good for a free evaluation board or evaluation kit up to $25, and you will be able to redeem these on the MPS website. So thanks very much for joining us, folks. Stay tuned for the next in our ongoing series of these EMI webinars. We'll be sending out invitations via email. Have a great day. Take care.